So welcome this evening, very warm welcome to our this edition of our lecture series, Bauhaus Design Positions. For those of you who don't know me, I'm Thomas Pierce. I'm Junior Professor of Emerging Technologies and Design here at the Faculty of, I'm telling you to address now, Emmanuel, you can't see me now, right? Maybe like this.
There you are.
There you go. Here at Bauhaus-Universität in Weimar. And today we're co-hosting this lecture with two other professorships from the architecture faculty. So we have the Konstruktives Entwerfen und Tragwerkslehre, Professor Michael Herrmann and his assistants, and Konstruktives Entwerfen und Erproben. I don't know how you translate those to English, or if I should. With the first professorship, we've had a collaboration for the last 2 years with Suko and Lucas, who unfortunately can't make it today, called irreguLAB, which is looking at how to use irregular materials in design and architecture using contemporary tools of scanning, programming, digital fabrication, etc. So very much, I guess, along the lines of what some of the things that Emmanuel will be showing us today. And I'm super excited today to welcome Emmanuel Vercruysse. He's joining us from the UK, from the Architectural Association in London or in Hooke Park or somewhere in some village in Devonshire. And for me this is really special because Emmanuel has been a mentor and a friend for the last kind of, I think, 15 years. He's, ever since I joined his studio at the Bartlett School of Architecture as a master's student back in the days. And he was running a studio with, together with Bob Scheel and Kate Davis, who's also already done a lecture in the context of Bauhaus Design Positions. It's on YouTube, go and look at it, it's fantastic. And what was really exciting, I think, about that studio is that we had a big kind of technological playground in the basement, central London, but a basement full of robots and CNC machines and 3D printers and what have you. And we could just play around, and we were encouraged to play around, also to use these tools not just as solutions for problems, but also as new ways of seeing, new ways of making, new ways of designing. So always kind of combining technological exploration with experimental design approaches. And I feel that now that I've kind of expressed that, I feel that a lot of the work that I'm doing with the students, or we are doing with the students at the professorship, comes, I think, from that time. So and the DNA lives on. So so as I said, very special moment to welcome Emmanuel, and I will maybe hand over to. Are you going to say a couple of official words or no? Okay, brilliant. Then I'm very happy. I'm very happy to do that as well, because that was the personal introduction. The less personal introduction, and sorry, Emmanuel, I don't know your bio by heart, but it's also on the website. But Emmanuel is a trained architect and partially also studied furniture design, if I remember correctly, before coming to London. He's taught in various institutions, amongst others at the Bartlett School of Architecture, but also now mainly at the Architectural Association at Hooke Park, which he'll be telling us about today. Hooke Park is an absolutely amazing place. Emmanuel has a dream job. He basically owns a forest and he can make buildings up from it live. They have a robot, they have a forester, they have local technicians, and it's an amazing place, and I've visited often, and I always really, really like being there. And I think it's not just special because of the context, but it's also special because of the people who are there and who run it and who really kind of drive this hands-on experimental agenda, building, learning through building for the students, right? Researching through building. And that was also the reason why I invited the other professorship for Konstruktives Entwerfen at Erproben to co-host this lecture because they concentrate on design through making, or design build, right? Design build, as you would call it. So I think without further ado, Emmanuel, the stage is yours, and I really look forward to your talk.
Yeah. All right. So Hooke Park. Yeah. As thank you, Thomas, so much for such a flattering introduction. I will start, as I usually do, with showing a video just to locate the work, because we can only do the things that we do because we are in the forest. So I'm just going to play this lovely little video. And I hope that comes across all right. Right, so I hope I give you a little bit of context. So We are located in Hooke Park. This is a map of Hooke Park. So Hooke is an industrial woodland, and it has up to 17 different species of trees. So this is our lovely campus. We're in the middle of it, and our mission with the student. You know now?
Yeah, perfect.
Okay, wicked. So yeah, we inhabit this industrial woodland, and it's really important to remember that this is a crop, right? So this is material that will be harvested in a certain cycle. So they have a 50-year cycle, and it is our research. It's a field of research. So the image that you're looking at the moment is not a render. It is actually a LiDAR scan. So we're combining airborne LiDAR scanning with ground-based LiDAR scanners to give us a holistic image of the forest. And so this means timber is our main material. And this lovely tree is not a Hooke Park. This is an angel oak somewhere in the States. But we use this as an example to demonstrate how incredible nature is in growing these fantastic complex structures. So if you would be a structural engineer, if you would have to make something like that, you'd be very much challenged. So we think nature is a really good designer, but this is what industry really makes of this material, and for good reason. It's really handy to have a predictable material which is uniform in size and dimensions, and you can predict its behavior. But we have all the equipment on site, which is part and parcel of timber production. So we have a sawmill on site, so we can decide what our geometry will look like. And if you look at a standing tree, if 40% to 50% makes it as a building component, that's seen as highly efficient. So our mission statement very much is to try and use everything from a tree. So there's two strands of research that are happening at Hooke Park. One is focusing on natural geometries. We're kind of in love with these really exciting curvatures and anomalies for timber production. Like timber production doesn't know what to do with these full geometries, but we know from an engineering point of view they're the strongest part of the tree. And this is not practices that we invent. This is an image from an encyclopedia from 1700. So back in the days, people would go out with a jig and go look for a specific bit of tree when they were building a boat or a house or a cathedral. So Hooke Park is a laboratory, and we are interested in every part of the tree, from the root plates all the way to the crown timber, and we will find applications for that. This tacit engagement with the material is very important to get hands-on and actually learn from it, learn from its structure, and we learn through making, we learn through the physical production. So one side is natural geometry, the other part is engineered timber. So practices like glulam and CLT, cross-laminated timber, means that you can reconfigure the tree into a specific diagram that aligns with the forces that you need this piece to respond to. So these are carefully choreographed recompositions of a tree, so we can make something which is stronger than the original tree. We're interested in different ways that we can manipulate timber. So this is steam bending. We can expose it to fire and heat to manipulate its shape. So in this case, this is pretty much like drawing with timber, right? It's very refined, so you can kind of control its behavior. Our toolbox is not really extensive, but scanning is very important, and I'm sure Thomas will point this out and you will have done exercises. But photogrammetry means Really, this method is a connective tissue between the digital and the physical realm. I just skipped. But it means that we can develop libraries of these natural geometries that we can then work with and develop. The other bit of kit which is really important is this young lady. This is Latoya, the 6-axis robot. KRC2 C150, so she was born in 1996, so very much last century, probably a lot older than you guys over there in the lecture hall. But she allows us to operate with the surgical precision on the natural geometry, so she's very important. And then the final piece, which is really important for us, is the ability to make our own tools. So the bandsaw that you are looking at is not something that you can buy off the shelves. We buy bandsaws of eBay and we will reconfigure it. So this bandsaw is generation 2 and this is generation 3. So we will optimize and learn from the tool. And this is pretty much the holy grail in the world of making and fabrication, if you can make your own tools. So it's a large part of my research to develop new robotic applications every year. This is by far the scariest tool that we ever attached onto a robot, the circular saw that rotates at 25,000 revs, so pretty evil tool. But I'll try to develop it every year. We try to develop a new one, and when we have a new tool, we try and get some bright minds from across the globe to come and play with it, and then we make little films like this to try and introduce people to come into it. And what it allows us, sorry. I thought someone was saying something. I like this image just because it really illustrates the juxtaposition between really precise junctions and connections and the power of leaving these natural geometries intact as much as we can. And it allows us to build crazy structures like this. And it's really important to understand why we do this. First of all, it reduces the embodied energy, right? We just locally operating. But second, and this is probably more important, natural geometries for the same section are about 30% stronger, which means if you cut things into a dimension, like a square, you're actually reducing the strength of it. So these things are really important in the way that we work, where we try to work with the natural geometries as much as possible. And this just really functions as a little demonstration that we work with all the parts of the tree. So when students join us, they don't necessarily have all the skill or the expertise to work with it. So we use these as kind of developing learning skills. So we gave the students this root plate and we taught a bit of robotics and a bit of CNC. And in the meantime, they made this lovely meeting table where the root plate is the structural system to the table, and there's some poetic notions of this island coming through the tabletop. It's a memory of the root plate. And then the role of the drawing is really important. The role of the drawing to seduce you to go make. So it's really important to understand how much information do you need from a drawing before you need to hit the workshop. And the workshop is the place where we do all the work pretty much. 90% of the time we need to be in a workshop. And that's where we make all our discoveries. And then this is Ankai. The other thing, you probably have seen him in the earlier movie. We set Ankai the single challenge to steam bend an entire tree. And the reason why I focus on Ankai is because one of the key things that we do at Hooke Park, we ask our students what practice do they want to form when they finish, what knowledge are they after. So the great thing about Ankai is that he is still doing the same thing that he did with us 10 years ago. He's still steam bending entire trees, making these most beautiful constellations. I could go on showing work from Ankai, but I want to show you some demonstrations of these principles. So the first one I'm going to talk about is the process that surrounds the field station. So this is working with timber in the round, and then I will also show what we can do with engineered timber. So this is the field station. It sits at the edge of our forest, and it's in a really important location because it overlooks the Mapperton estate. And so this is its site. And the story of the field station is related to the industrial harvesting process. So this is a very intelligent machine that roams our forest. It's an industrial harvester, cuts down a tree in less than a minute. So it will grab the tree, the chainsaw will cut it, it will flip it horizontally, and the head will cut off all the branches. As it does that, there are potentiometers in the head that are measuring the diameter, and on its way back, the algorithm, which are based on market information, have already decided optimized length of this timber. So it's quite a scary machine, highly automated, but this is what it leaves behind. So it's a bit of a war zone. There's lots of really amazing material which is discarded by the timber industry. So we challenge our students to work with this material. So here they are scavenging for material, and we decided to build a 100 square meter roof structure using this material. So this is the star of the show, this humble beech branch. It's 50 to 70 mil in diameter. No one's interested in this material as a structural component. So you see it here in the context. This piece is used in compression, so it's quite easy to detail. It just needs some two tenons. And this is the global structure. So two frames of dimensional timber with the diagonals, which are the beech branches caught between, which provide a very stiffened truss frame. For us to be able to do that, we needed 256 of these components. For them to perform in a uniform manner, they all have to be the same length. So this is the robotic application that we defined for this. We made a feeding station so we could put all the stock material, pass it on to Latoya from outside the cell. We gave Latoya one eye, which is a 3D camera, and we mounted the circular saw onto a lathe, as you do. And this is what it looks like in action. So the structured light is not a visual gizmo. It delivers a mesh from every individual branch that it scans. So we had to repeat this process 256 times. So it took us about 2 months to develop this application. And we used dimensional timber to just calibrate the system, and we got the resolution below 0.5 millimeter, which is pretty crazy because this is green timber. But this film shows you the affordance of having an indexable blade because it really overrides many singularities or reach issues with the robot. And then it took Latoya 6 minutes to make a single piece. And as you can tell, we made a hole in the door, we put a slide in, and every 6 minutes one of these components comes out of the door. And this shows you really the scripting process. So from a scan, we can draw a circle. We have a mesh, we can draw circles. If we can draw circles, we can connect center points. If we have a center point, we just need to move the tenon geometry onto that central line. So we have to do that for every single piece. And this lovely animation kind of shows you that workflow here. So every tool path was unique for every piece. We have data for every piece. And the way that we work is really we learn through fabrication. We learn through making. So the first node I asked the students to make, I gave them some duct tape and some hot glue and some sticks, and they had 2 hours to make the first node. So that was generation 0, they called it, because it was very wonky. But by generation 7, we have a fully fleshed out building. So this is us doing a test assembly in our workshop. And these are all the components. So this whole structure is flat packable. So most of the components are interchangeable. There are no mechanical fixings. So we can take this apart and build this back up. We have a lovely relationship in kind with Arab. So they will help us with signing off our buildings and helping us calculate the structures, because all our buildings and all our structures need to meet building regulations and planning information. So all that needs to be provided. So we have a relationship in kind. We don't pay them, but in return they come and play with us in the forest twice a year. But this is what they gave us for the field station. So every node is a threaded rod that needed attention to a fixed Newton value. And then this is the structure. I love this picture because it's got a memory of the crown of the timber of the forest. It's got a memory of the forest located essentially into the roof structure. So we spent 2 glorious weeks on site installing it, and this is how it looks like now. So that was working with natural geometries. So I want to unpack the workflow for dimensional timber, and this is the skeleton that we built, primary structure, the superstructure for our large Wakeford Hall building that we are in the middle of building. So as you know by now, I will just show you the video. Right, so the project pretty much always starts with a sketch. So for us, it's really important that we find a way to set constraints for the students to be able to get creative as quickly as possible. So this is one of the sketches that were issued. And together with the sketch was a brief that defined the workflow. So the workflow that the students had to use was glue lamination and CLT practices, and use Latoya with a bandsaw attached to it. Now this workflow is intentional because it was perfectly scalable. So what you're looking at is CNC'd glue lam components. So they would mimic this workflow at a smaller scale, and it allows us, you can see the red annotation, it allowed us to draw onto the model, and that would inform the next generation of, well, the next information for the model, really. It took us 34 generations to get to this final model. And this is really because we could not afford for it to go wrong at a one-to-one scale. So we operate as a practice. We have to go through planning permission, so we do have to produce the general arrangement, like plans and sections and elevations, which is the normal kind of or comfortable terrain for the architect. But because we are also the fabricator, we produce information for production. And this is where it gets really exciting. So at the bottom line, you can see the design evolution of this one piece. This is informed, of course, by aesthetics, engineering evaluations, but also the dimensions and the reach of the tool. So if you look at the larger kind of drawing, you maybe just make out some red drawings, and that's actually the plan of the bandsaw. So if the bandsaw can't access the geometry, we can't make it. So there's a beautiful affordance in being the designer and the fabricator and the architect and the installer all in one. A beautiful closed loop. So this is the close up. And then obviously we face the reality of machining this. So Latoya has a reach of 2.5 meters. Some of these components are in excess of 5 meters. So then the information that you need to draw looks a bit like this. And this is the choreography of the piece, so the rotation of the piece that's required for us to be able to cut all these different faces. So that's quite important bit of information, to produce and to test and to figure out before you actually start the construction. And then you still get into issues where you're trying to do this undercut and the robot's completely folded up. But anyway, we managed to produce these really large scale pieces. And then a lot of the things that we do don't have precedence. So we'll try and we have to develop our own tests. So we try and test things to destruction. Arab will give us a value, and most commonly we will use, you see the left-hand corner, this is our heaviest machine. This is a telehandler, 8,000 kilos worth of evil machine, and we will try and break this piece. So we bolt it to the ground, we put targets on, and we have a load cell in between this piece and the telehandler, so we could understand, we can correlate the movement and the distortions in relationship to the force that's exhausting these pieces. And then we assemble and install it. So I'm sure you understand the complex relationship that timber has with moisture. So you can see this, we panicked a little bit, so we all jumped in the car, go to the co-op and bought up all the cling film. So we wrapped this entire piece in cling film to protect it from the weather, because we knew we wouldn't be able to build the skin for another 12 months, right? And this is quite a complicated exercise. So one group of students build the primary structure, and the next student needs to build the skin for this structure. So you can see the complexity of these nodes. Where do you start? And this is really where our scanning methodology comes back into play. We are not really that interested in the Rhino model. We are interested in information as built. So this is a really fascinating image where the Rhino model and the scan data is collapsed, so we can understand where the deviation is, where did we lose traction, where did we lose control, where did we make mistakes, how does the material behave. And then the second cohort, the students build the skin for it. And this is kind of how the state of this building at the moment. So that's two phases of students, some internal views. And this is a view by night. I like the way the dinosaur just revealed itself. You could just make out the silhouette when it's backlit. But this is the phase that we developed for the last year and a half, which is called the tree in the truss. This is the third phase of a 5-phase building. So we will have a lecture hall and exhibition space underneath that. But the tree and the truss are the main components that the students of 2 generations ago built. And this is a hybrid structure where it combines natural, so as you can see in this image, combining natural geometry and engineered timber. And this is the brief. I like showing the way that we work. So this is the brief that the students got issued. So you can see the sketch that I provided is quite close. It identifies all the key issues that need to be resolved, all the key design opportunities. And the reason that we do that, after this brief, this is the work within 2 or 3 weeks, students can develop these quite complex models. So it's a fallacy that the architectural education, this fantasy that architectural education creates, that you can spend 6 to 9 months within a design phase. So we need to move fast because we need to build this. So what we do within the course is we remove this idea of a simulation. We are actually going to build these structures. So let's have a look at this video. shortcut a minute, but I've still got quite a few things I want to show you. So this is quite an interesting display of all the different processes that are involved. So the blue bits and foundation, they are cedar, and then we use the natural tree as a column. That's what so they all have these quite bespoke workflows to make these pieces. So the first piece we will see in the robot used the industrial chainsaw to cut these faceted cedar pieces. Cedar is very good in wet or moist conditions, so this piece really protects the beech tree, which is a species which is very susceptible to moisture, so we have to protect it. This detail is really important because when we design, the most important question for us really is how do we assemble and how do we disassemble these structures. So everything, this entire project is 100% timber, and it doesn't use any mechanical fixings. So you can take this whole building, this whole structure apart just with a mallet, with a hammer. So everything is tensioned together with these with these splices. So it's really important. We don't believe that the wrecking ball is the answer to take our buildings apart. So these wedges, if you need more tension, you just hammer the wedge a bit deeper. If it's cracking, you need to release it, you just reverse it. So if a component fails, we can just prop the building and replace every component very, very simply. So then we use 10 trees, and every tree is unique. So 10 natural forking trees, which means we have to make a bespoke bit of glue lam for every piece, for every tree. So every piece is unique to the tree. So again, we use the chainsaw to cut these geometries. And then we make quite straightforward truss. So, and I hope you will have spotted that there's quite a bit of repeated methods and workflow. So we're really keen on producing a cumulative research. So we kind of keep building upon the research. Now, if you understand how a truss work from an engineering point of view, your first diagonal will be in compression, and then the next one needs to be in tension. So this is our tension web. Timber in tension is very strong. The problem is always how do you hold on to it? Because as soon as you drill into it, or if you remove material, you make it weaker. So our solution here was to curve cut it, steam bed it, and introduce these wedges. So then we could hold on to it just to its altered geometry. And as usual, there's very few or no precedents for this. So we have to develop our own structural tests because Arab said this humble bit of timber needs to withstand 4 tons of tensile force, which is enormous, really. So you can see, if you look at the reader, at about 3 tons, the grain is collapsing and we are pulling this geometry through. And this is because the splayed geometry, the tension web, that's beech, which is a hardwood, but the dimensional timber of the truss is spruce, which is a softwood, so the fiber would just collapse. So this is a design opportunity for us. So what we did is we made a little pocket and we inserted like a prosthetic bit of hardwood that would deal with the forces just locally. And that solved the problem when we got to the required newtons that Arab were after, so we could carry on assembling and producing. So we just made 5 of these axes, and we hope to install them after the new year, which is pretty exciting. And these are the gangsters that we did it with. So these lovely people spend about 12 months building and developing this work for building all these structures. I want to end with showing you the forest datum, which is the project that we finished last year. And this is a really important project. For us, it changes a lot of things. As usual, I will just start with the video and then we can unpack the process. Before the video, I want to show you this, which is a little sketch. So every project starts with a visual illustration of where we're going, what we're trying to do. So we're trying to use as much of the crown wood as possible, use the whole tree. This was the mission. And this is the video. Okay, so let me see. Yeah, so this is the main material for our structure of the datum. So we're really interested in this as a structural system for the floor or for roofs. So this timber is described in forestry as juvenile timber. So it's kind of like the teenagers of the timber. It's very unpredictable in its material behavior. What's really important for us is that this project does not require us to cut down a tree. We can get most of our material out of the standing trees. So we get our material through high pruning. So this relates to indigenous practices. And kind of from a structural logic, we are always looking for this simple basic cell. So this is the basic cell, the basic bounding box that we put our juvenile timbers into, and then we reduce it to XYZ values that are all the same. So what's important within this project is that all the intelligence resides within the jig. So it doesn't any longer require a 6-axis robotic system. So we are really interested in working with local communities, because the only thing we need to make the structure is this jig and a bandsaw, which changes things, right? And the structural logic is such that these geometries are too small. You can't cut any timber joints in there. There are any kind of lap joints or scarf joints or mortise tenons. There is just not enough material. So they have to rest against each other in compression. And then we get a bit of dimensional timber to hold all these pieces in place. And again, we learn through making. This is the very first jig, right? So we set these principles out, and then the very first jig takes about 2 hours to make. And this is the final jig, right, which has been optimized. It's quite an intelligent little piece with lots of 3D printed components. Now, it's important to understand that these 3D printed components do not alter the geometry. They are there to support the timber, because we have to avoid any kind of vibration or moving when this piece is being cut. So that's the supporting role of the 3D printed components. And then we are really interested in the morphology of a tree. Every tree branches differently. And as a designer, we want the material to lead, so we take a step back. So when we did a scan of beech tree, we are running an analysis, and we are looking for the most common geometries. So the most appearing angle and fork geometry. And that determines our X, Y, Z of our jig. So we're trying to let the material take all the decisions. And this is really a pleasant way of working as a designer, because we are just following the material lead. So here they are, they all rolling into this configuration. And then we use a bit of Dyneema rope, which is 10 times stronger than steel, to bring all of this geometry into tension. So this is pretty much like you can see this as a pre-tension component, like they would be as you have pre-stressed concrete. So we could turn this into a banana if we so want to anticipate a potential load case. So here are some images of it on site. So the timber that we used for this is beech. So the stupidest thing you could do is put it outside in Dorset, because beech is so susceptible to moisture. But we are a laboratory, and we are interested in failure. So we want to see how this piece behaves. And the interesting thing is these branches take about 3 to 5 years to grow. So if we could make this structure last 3 to 5 years, then we have a perfect circle. And this connects with pedagogical concepts, like you all know of the Eisi Temple in Japan, that they rebuild every 40 years. So I'm very happy to rebuild this structure, take out the soft tissue of these branches, and learn another cohort how to construct this piece. So this datum is part of our camping facilities, because we're a bit too popular. Too many people want to come and stay with us, so we're developing camping facilities. This datum is a boardwalk that will lead us to the showers. But I love this image. So this kind of talks about scanning the crown timber, running an analysis, cutting out all the little forks that we need without killing the tree, and then part of the assembly process. And as I said, this will lead to our showers. This is the wild thing. This is kind of where this this piece resides now. And we've just gone to install it next to the datum. So you can see the idea is not that you jump, but the platform on the right hand side will provide 2 showers with a beautiful forests view. The way to get to the showers, there are 2 drawbridges, and we're interested in this state change. So the drawbridge, you walk across it when you're in the shower, you pull up the drawbridge and it becomes a door that disconnects it from the jetty. That gives you privacy. So this is kind of where these last projects reside. And as I mentioned, we're really interested in accumulative research and kind of pushing the boundaries. So if the datum was a horizontal structure, we questioned our students, how does this behave vertically? So this is Luxai's work, looking at the facade system with exactly the same forks, exactly the same jig used to cutting it. But because of the inverted force relationship, there's quite a bit of metal in there, but quite a beautiful, elegant system. Right. And then I will unashamedly advertise, if you are interested in this work, you can come and play with us 2 weeks a year in the summer. We just drop you into this workflow and you can come and play. And I think I will leave it at that.